can transfer our higher order equations into first order set of first order equations. Now, at the beginning of the chapter, you see that title of the chapter was Rangakuta methods. Actually, whatever method we have learned so far all belongs to a general category called Rangakuta method. So today what I will do, I will be gradually going from a general perspective to all these methods. Then we will go to Rangakuta standard technique. Then try to conclude our lecture today with simultaneous solution of differential equation with an example from your earlier learning. Okay, so this is your text. Okay, we have discussed the earlier things in our last class. Okay, we can again recap the thing starting from equation 25.36. Actually, what this is also a general the Huon's method described in the general perspective of Rangakuta method. Okay, so you see that in all of our method that we discussed so far, actually are called one-step method, that we are using our starting point and proceeding further, and in such a way that the slope that is involved in your first order differential equation is actually approximated in such a way that your numerical error will be minimum, or your solution will be approaching to your actual value. In your Euler's technique, your slope is estimated at the beginning. In the Huon's method, your slope is averaged. In your midpoint method, your slope is calculated at the midpoint, and that is considered to be valid over the entire length of the segment. And probably we have discussed about these key methods earlier. Then by using that, actually all this thing depends on how your slope is approximated. So you see that in equation 225.3 Huon's method, you see that your slope is averaged. Okay, your K1 is the slope calculated at the starting point. K2 is the slope calculated at the endpoints, and they are averaged. You see that the weight factor of your K1 is 0.5 and that of K2 is also 0.5. Then if you want to go to the midpoint method, in the midpoint technique, you see that your slope is calculated at the midpoint. Your K1 will be there. That K1 is not involved in your algorithm. Your algorithm contains K2, that is the improved slope estimate made by 25.37 at the half steps in your half step or midpoint. Another technique is called Ralston method. This method is this. Okay, here in this case, your slope is estimated weighted. The first slope, K1 calculated the starting point is weighted by 1/3. And your next slope calculated at the 3/4 of your step size is weighted by 2/3. And this is what you have in this example. You try to redo this example and you see and compare by using this figure. This is very simple to be calculated. Okay, I will be showing the thing with what we call a bit broader perspective by using a fourth order Rangakuta method, and leaving 23.32 for you to go through it. The reason is that if we are getting accustomed to the fourth order method, then this third order method can easily be understood then. Okay, for this reason, I am skipping this. So the fourth order Rangakuta method, this is what the standard Rangakuta method we generally solve or use to solve a huge number of, okay, many types of differential equation. Okay, again, you will see that your K's are actually related to the slope. How many slopes are involved there in equation 25.40? You have four slopes are involved, but altogether your weight factor is not same. As a result, the interior points slopes are weighted by 2. As a result, actually 6 slope values are involved in this equation, and we are dividing it by 6. So this is the average of 6 slopes. And this is actually nothing but an improved version of approximation of the slope. Then we are calculating the slope average, then multiplying it with exercise. Then the algorithm is very similar to your Euler one. Your old value, a new value equal to old value plus slope multiplied by age. But it is not the slope calculated at the beginning, but we are calculating 4 slopes and weighting the interior K2 and K3 by 2, then taking the average. Then how to proceed with calculating K1 and through K4. You see that your K1 is calculated at the starting point. If you stop here and do not use averaging, this is your Euler method, standard naive Euler method, okay? Now, if we want to go to calculate our K2, your K2 is calculated at a point where we are calculating K2 at a point, that point is equal to the point you start with plus half of the step size, isn't it? Let me show it figuratively, okay? Say we are here, this is your xi. Then if this is your xi plus 1, our intention is what? We have to calculate the value. This is your y, okay? We have to calculate the value y there, that is yi plus 1. This is the value of your y in the next time step. So you need to calculate the slope. We don't know how to calculate, in what ways your function is varying. Your function may vary in this way, okay? So what will happen then? We will again be calculating our slope at this point. That point is equal to xi plus h divided by 2. In order to calculate the slope at this point, don't you know the value of your function at this point? Y xi plus h by 2, don't you need the value?
Yes, sir.
We need the value. If you want to calculate that value is calculated to be something like this, okay? That means the initial value yi plus slope K1 multiplied divided by h divided by 2. You got the point?
Yes, sir.
So this is what the value of y we are calculating. That value of y and the value of x will be used to calculate the slope K2. In the same way, you can proceed in calculate. Then one just important thing you can notice here, that in calculating K1, K2, your K1 is involved there. Then you can calculate your K3 at the same value of x, but with a different value of your y. That means we are calculating y by using a slope that we calculated in the earlier step, K2. In this way, K3 is calculated. So your K1 is involved in K2, and your K2 is involved in K3, and your last slope is calculated in this way with full step size using the value of K3. So we are starting with K1 initial, then K2, then K3, then K4. So your K1 will be involved in K2, K2 will be involved in K3, K3 is there. In all these cases, your step size is h by 2, but here your step size is full. Then the algorithm is very simple, that yi plus 1 would be equal to yi plus 1 divided by 6 into K1 plus K4 into 2 into K2 plus K3. In this way, we can proceed with calculating. Okay, an example is there. Actually, 2 examples are there of 2 different types actually, just to illustrate this technique. Okay, one example is where your slope is not the function of independent variable, a dependent variable. Another example is where your slope is depending on the both variables. That means you may have your differential equation dy by dx, that is the function of x only, or you can have your differential equation dy by dx with the function of x and y, both. Okay. In example, okay, we'll be showing this algorithm. Okay, you can apply this in your equations of your subject area. that we have discussed in our last class. Okay, if you have a first order equation available with us from an electrical circuit or an operational amplifier, you can apply them there and try to verify how things will work. Okay, lots of algorithms are actually there in differential equation solving. As this is an introductory course, we cannot, for example, go to the deep detail for each method because this needs another dedicated course for solving differential equation numerically. For this region, some of the standard methods we are introducing to you with the hope that if you can apply them properly in your learning, then on top of it, you can grow and proceed of using some other variants of your numerical algorithms. You see that your first one, is it not, although a function xy is written there, is it the function of x and y? It is simply a function of x, isn't it?
Yes, sir.
So this differential equation is dy by dx is equal to fx. Okay, anybody can solve it by simple integration. Your initial values are given, and this is your step size. Okay, this is one problem. Another problem is what? You have a problem there. You see both your independent and dependent variable are involved, isn't it? Your initial values are given, and you have been asked to solve from 0 to 2, actually one step. As your h is equal to 0.1 and you have been solved for x equal to 0 to 0.5, then how many steps are there within this range? Is it not only one step?
Yes, sir.
Now the thing is that if you want to go through it, how many, using our fourth order arcade, there are how many slopes you need to calculate? K1, K2, K3, K4, isn't it? K1 equal to what? K1 would be equal to F into the initial point in our case. Our initial point was x equal to 0. So you calculate F0. This is simply equal to put x equal to 0 there, then you will find your K0. This is what your K1, okay? If you want to find K2, then what you need to do? You have to calculate your F at where? Xi plus h by 2. So xi equal to 0, initial point, plus your h equal to 0.25, h by 2, isn't it? So you calculate your f.25. So this is what your f.25. Next step is what? You have to calculate your K3. K3 is again to be calculated at the same point, okay? x0 plus 0.25. So the same here your K2 and K3 are same. Your K4 is to be calculated at full step size equal to 0.5. So this is what the value of your K4. Now the thing is that this is simple. The reason is that in calculating your F values, you do not need Y. For this reason, your calculations are simple. So if you have your all your slope values K1 through K4 are with you, then you average it by dividing it by 6, multiply it by step size, and add this thing with the initial value. This is what your Y at 0.5. That means yi plus 1 is equal to yi plus this thing. Okay. Here your I is first step is y0. There your next step is y.5. So you y.5 equal to y0 plus 1 by 6 into all this average of all 6 slopes. So in this way, you calculated your 0.5. Then if you want to calculate it at at y1, then what you need to do? You have to repeat this procedure with your xi values replaced by, initially it was 0, now it will be equal to 0.25. That means in the next step, your K1 should be calculated at 8.5. Your K2 should be calculated at 8.75. Your K2 and K3 should be calculated at 8.75, and your K4 should be calculated at what? F1, isn't it?
Yes, sir.
So then again, you will have 6 values of your K, average it by dividing it by 6, multiply it by 0.5, Then you add the value of y05 that you calculated in the previous step. Then you will have your next time step value available to you. In this way, you can proceed with solving your equation for that time step. Okay. Now let us illustrate the second thing, where your equation slope will involve. You see that this equation of this type, okay, dy by dx is equal to function of xy. Is it not the thing? Because your equation was this, and that is what equal to you dy by dx. So your function xy is equal to 4 into e to the power 0.8x minus 0.5 into y. How many initial values are needed? You need the initial value a of x at x equal to 0. What is the value of y? That is also given. Are not those things given? The value of x equal to 0, y equal to 2, step size equal to 0.5. Okay. Do you need any more information in proceeding with? You do not need. Then you proceed in calculating the 4 slope values. What will be the values of the 4 slopes? K1 equal to what? K1 should be calculated at which point? At the initial point, isn't it?
It's equals to 0.
Yeah. K1 should be calculated by using the beginning point of a step. So your K1 is equal to f into xi yi. In our case, initial case is equal to x equal to 0 and the value of y at 0, isn't it? And that is equal to f0 and the value of y was given 2. So you have to evaluate this quantity. This will be equal to K1. And that is what that quantity. Okay. Is it okay?
So
The next step is what? Next step is you have to calculate the value of K2. K2 equal to what? F xi plus h divided by 2 into yi plus K1 into h by 2, isn't it?
yes, sir.
Now, this quantity is available to you. It will be equal to 0 plus 0.25 equal to 0.25. So this is equal to 0.25. What is the value of this? You have to calculate. K1 is available from this step. Your yi is available for the initial step. So this is what that value. Yi will be coming from y0. And this is the value of is k that we calculated in the first step. This is your h by 2. So this is the value of y 0.05. This is what? This is actually y at what? Y at, this is h by 2, y at I plus h by 2. That yi plus h by 2 is nothing but y, in our case, xi equal to 0. So it is equal to 0.25. So this is nothing but 0.25. So your K2 would be equal to this. This is the value of your x I plus h by 2. This is the value of your yi plus K1 into h by 2. With these two values, this is you replace your y in the slope equation by this. You replace your x in the slope equation by this. This is your y. This is your x. Then this is what the value of K2. Now, if you want to calculate our the next value, in calculating the next value, again you have to apply this. Your x value would be equal to x0 plus h divided by 2, and that will be remaining as 0.25. So this will be remaining 0.25. But we need a value y. That yi should be calculated as K2 into h divided by 2, isn't it?
Yes, sir.
So your K2 is already available here. So you put your K2 there and you calculate the value. Then this is what the value of your y at 0.5, okay? So using, no. This is the value of your y at this point, then you calculate your K3. Then in calculating our K4, what you need to do, you have to have your full step size xi plus h. In our case, 0 plus 0.5 equal to 0.5. Now we have to calculate our y I plus K3 into h, isn't it?
Yes, sir.
So by using this thing, you can easily, I hope you understand this thing, very simple to be calculated. Okay. So once these 4 Ks are available, you see that when your function will be, when your derivative or slope will be the function of both independent and dependent variable, your solution will take longer time. So your things are calculated. So y point value is this. Okay, you see that how accurate the thing is that. If you want to compare it with your original solution, you see that it is accurate up to the 4 significant points, isn't it? 3.751, 3.751. So some higher order methods of Rangakuta is also available. Okay, you can try it. But if you want to go through the higher order method, actually, sometimes it is very difficult to implement the thing by using hand calculator. So see, you can program it. A comparison is there, how your error is changing with the different technique. So with this thing, I will be going to this interesting thing, system of equations. Okay. Actually, the thing is that at this point, let me ask you one question from your earlier learning. Okay, in your differential equation course in first year or second year, when you solve your differential equation, did you solve simultaneous differential equation?
Yes, sir.
Okay, how did you do that? Can you remember? Analytically, of course, but the technique was what? Actually, there exist many techniques, okay? But some of the widely used technique is if we can represent our equations by using operator technique, this is very good. Do you know how to represent differential equation by operator? For example, if we have an equation, say d2y dx2 plus say a into dy by dt dx plus say by equal to c. If you want to write this equation in the operator form, sometimes we write this equation in this way, d2y plus a dy plus by equal to say c. Have you seen this form of equation in your text?
Yes, sir.
D equal to what? Your D is simply the differential operator, isn't it?
Yes, sir.
You cannot write yd. You have to write dy. Okay. The reason is that this is not a multiplication, so that you cannot commute. Okay. Your operator. This is your operator. Okay. This is your operator, and this quantity is called operand. Okay. Your operand cannot precede the operator. This is not an algebraic equation. This is equation. Okay. But this can help us in solving our simultaneous differential equation very easily. Okay, can you convert this equation into 2 first order equations? This is a second order equation. So far, we did not learn anything about solving second order equation numerically. Okay, let me proceed to using whiteboard. Our equation was, I am asking you just to convert this equation dx2 plus a dy by dx. You guys, this is your first year problem, okay? Do not remain silent, then it will be a big question for you about the investment of time and money. This is a, what is the order of this equation? Is it not a second order equation?
Yes, sir.
Can you express it in the form of first order? For example, if we change the variable in this way, consider that u equal to dy by dt. Then with the help of u, can you write this equation? It will be equal to du by dt plus a into u plus by would be equal to C. Then you can have your two equations there. One, you dy by dt equal to u. Another equation is there, du by dt is equal to C minus AU minus BY. Are these two equations not the equivalent of this second order equation?
Yes, sir.
Then you see that a second order equation, even the higher order equation can also be transferred into a set of first order equations. If this is possible, then we can easily apply our first order solution technique to solve the equation simultaneously. Now the question is there, in order to do that, what you need to do, if we want to write the equation in the operator form, our objective is what? Our objective is what? We have to solve for yx. That we need. But in solving this thing, we are also migrating a function or using a function ux that is coming as an intermediate variable to us mathematically. But in practice, this might have some association with physical quantities in a system. But if you want to, for example, write the equation in operator form, can we write this? In your first equation, you can write this, that dy minus u equal to 0. The second equation can be written as what? D2y plus au plus by is equal to c. Can we write this?
Sir.
Our objective is what? We have to solve for u and y and u. Can we put the thing in the matrix form in this way? This is your y, this is your u. And you have your another side, something there. You see that in your first equation, d will be coming here and your u position will be equal to -1 and no value is there in your right side. And in the second case, your y is there as d2 and your a is there, no, d2 plus b. Okay, because your b is there. And you have your a there, okay? And that is equal to c. Is it not your equation in the matrix form?
Yes, sir.
Okay, if it is in the matrix form, can you solve it for y?
Yes, sir.
What do you, how to do that? Your y would be equal to what? Your y would be equal to, we will have a determinant there. That determinant is d -1 d2, which is not d square. Be careful about that. This is d2, double of differential derivative a. This is, and here in this case, you have to replace your first column by 0c. Then your second column will be, this is what your Cramer's rule, is it not?
Yes, sir.
Then your solution would be equal to what? This equation can be written as, okay, simple, this would be equal to C divided by, you see that A is a constant, you can write it AD minus D2 minus B, isn't it? Then from this point ahead, you can proceed with solving your equation with the help of your learning earlier, okay? Because you see that this is nothing, we arrived at the equation that you can factorize it, you can partially differentiate it, no problem. But only thing is that your manipulation will not take the form of algebraic manipulation. It is your operator, okay? Take help of any text that you followed in your differential equation. Which text you have you followed in your undergraduate level for solving differential equation?
Sir, Sadiku. Chapter 7.
In first year differential equation mathematics course, did you follow Sadiku?
No, sir.
What was the name of the writer? Actually, thing is that, okay, at the beginning of my course, I said that electrical engineers, not only electrical engineers, engineers are not mathematicians. For this reason, actually, but mathematics is the language of engineers. If you do not know mathematics, then there is no any value of your learning. Be careful about that. But you do not need to know that many mathematics that others are doing, like the pure mathematician. For this reason, there are some texts, and our library is full of such texts. At least I introduced 2 or 3 texts in this library. Those texts are worldwide used. Even in MIT, they are using it. Even in many other universities, they are using it. I introduced many texts in this university. But unfortunately, teachers are not going to it. This is the problem with the internet, okay? They simply copy something from somewhere or get some lecture note from somewhere. They simply replicate it. And even in many of the courses, if I ask the name of the article text, although in their course plan, they are mentioning the name of some text, but they are not using it. I am not sure actually, but I know that few are doing it. If they are not introducing you something and you are not enthusiastic one, then nobody will introduce you with some novel article or some good something that others are following. In your library, you have some text that they are dedicatedly written for engineering students. The name of the title of the text are something like this: Mathematics for Engineers and Scientists. Why they have written this text, name engineers and scientists? That means those mathematics are dedicatedly applied for engineering discipline. Have you heard the name of any book of this title? No. Then how you will find the relationship or learning, for example, significance of learning mathematics as an engineer? You will never find this thing, okay? So forget about this. But
Sir,
some
we
of
actually,
the,
sir, we actually learned from the Dennis G. Gill's book, sir.
Dennis Gill's book.
Sir, Dennis G. Gill.
Okay, then,
An introduction to differential, first course into differential equations.
that was okay. But this book is purely written for pure mathematician, okay? But you have a book named by Ross, R-O-S-S, okay? And that book is written for engineers. And you have a text written by KG. That text is dedicated written for engineers. You have some books, Greensburg. That book is dedicatedly written for engineers, okay? So those books are being followed in many world-class universities who are on the top of the ranking list. So I try to get some flavor of it if you have some time, okay? Otherwise, you will see that many things will remain invisible to you. Okay, then you can pick one of the texts and try to learn how theoretically you can handle this. But now what we will be doing, that let us apply this thing in our practical problem, and how can we solve this by using the algorithms we have learned so far. One of the nicest example and most simplest one that we can start with is simple RLC circuit. Okay, you know that from the earlier courses that if we have a single energy storage element in your system, then your system will give you a differential equation of first order. Then you can calculate quantities like current, voltage, whatever it may be related to your circuit using by solving the first order equation, okay? And you see that the differential equation will always be involved when a circuit will change its state. In the steady state, a differential equation is not needed. But if we assume that we are applying something there, EUT, this signifies that if your circuit was, for example, in the relaxed mode, nothing was there, that means no current was flowing through your circuit. Say we are considering this state I0 minus and BC say 0 minus. BC is the voltage across this capacitor. Consider it BC, this is C. This is equal to 0. Then this source is applied. This signifies that you are using a source. That source has this nature, okay? This is T, this is UT, you know what is a step function. So it is applied at t equal to 0. Then you have been asked to proceed with calculating your current and voltage, whatever it may be, for time t is greater than equal to 0. And in the last class or earlier in it, we derived a differential equation considering that voltage across your capacitor is the output. And I hope you can remember this. And that equation was something like this. Not something actually exactly like this, okay? Can you remember this equation that we derived in the last class or earlier?
Yes, sir.
Okay. Is it not a second order equation?
Yes, sir.
So if we want to apply our first order algorithm there, what we need to do, we have to, for example, split this equation into two first order equations. That actually we can easily do. We know that our capacitor current dVc divided by dt is simply equal to I divided by C. And in the same way, we can write our inductor current dt is equal to what? E divided by L minus R into I divided by L minus what? Our equation was minus E plus L di by dt plus Ri is equal to, plus Vc equal to 0. Then you divide all the way by CL, isn't
So
not the
VC by
case?
L.
Now, how many equations we have then?
Two equations.
Are not they simultaneous?
Yes, sir.
If they are simultaneous, then can we solve it by using
Yes,
the
sir. We
initial
can go
values?
for that Cramer's rule, sir.
How to apply your Cramer's rule again there? You can solve the thing numerically. If you want to solve the thing numerically, apply any one of the algorithms that you have learned earlier in solving first order differential equation in a simultaneous way. For example, if you want to solve equations for consider that we need to solve for, first we start with our solving for VC1. So the algorithm for solving VC1 you can write in this way. VC say VC I plus 1 would be equal to what? VCI plus slope. What is the slope actually? Is it not the slope?
Yes, sir.
You can consider this slope at I divided by C multiplied by A. Is it not
Yes.
the algorithm for solving your first Euler algorithm for solving your first equation?
Yes, sir.
For your next equation, I plus 1 would be equal to what? I plus your slope is whole thing is your slope is equal to E divided by L minus R into II divided by L minus VCI divided by L. Is it not the thing?
So multiplied by steps.
Okay. Then you apply this calculation recursively in your equation, and you will find the solution there that will give you the voltage and current solution for a particular value for values of E, R, L, and C. In this way, we can solve our simultaneous equation there. Okay, you try to redo the example by your own, and you can write your code by yourself to solve your problem. Or even in MATLAB, you have your built-in algorithm there. How many algorithms you have learned so far from MATLAB? Have you learned about ODE45 or ODE23? Not yet.
Not yet, sir.
Okay, try to explore it. All these implement there. Now you will find another class of equation, ODE probably another algorithm S or something like this. This is also available. I will discuss about it later when we are using another type of our problem that is called steep system. So this is what the introduction. Now with this value, we can solve it. We can write our MATLAB code, or even you can apply your Excel to solve it. Okay, I will be showing this. In the last class, I have shown you how to use Excel to solve our differential equation by applying a simple formula there in the Excel spreadsheet cells. Okay, after my last lecture, did you open up your textbook or, for example, use Excel at least to explore something? No response. This signifies that you could not find that time. One of the CRs, okay, give a post there, okay, that their week is very hectic. I don't know in what ways you are making your week hectic. Okay, so you did just want to just shift your thing. Why you thing was so hectic? How many jobs are there that you need to perform with the weekend? In the student life, you cannot make your life hectic, then your investment has no value. Be careful like that. Okay, student life is not the place for sleeping and dining and enjoying. Okay, you try to get accustomed to it, how to cope with hectic situations. So the thing is that if you want to solve this thing, I have simply written this recursive formula there for an RLC circuit. Okay, with initial values are set to 0. We solve two equations there with initial value given in this column. This is the initial value of your current. This is the initial value of your voltage across capacitor. The value of R is set in this cell. Value of L is set in this cell. Value of C is set in this cell. Value of E are set in this cell. Okay, those cell values are actually replicated in the used in the algorithm in such a way that your cell address will not change there. I don't know whether you know how to address a cell when cell value is not changing, okay? But try to explore it. So this is what our first equation, you see, because our B cell corresponds to current, your C cell corresponds to voltage across capacitor. So you see that C cell is taking a value B4 that is coming from this initial value. And this is your step size. And all these values are E, the I values and VC values divided by the cell address of B2. And that cell address is made in this $sign in this way, so that this cell address will not change if we copy the formula elsewhere in our spreadsheet. So this means this is the thing equal to E minus R divided by E minus Ri minus C divided by L, and with the initial value B0 there. That means this is what the equation, recursive equation for your current of RLC circuit. This is the recursive equation for your voltage. Okay, C4 is the initial voltage given there, and this is what your step size, and this is the current we are using. Actually, it should be B4. Why I put B5, I will discuss later. Let us put B5 there first. Okay, this is B5, no, B4, the initial value of your current. You know, the equation is dVC by dt equal to I divided by C. This is what your equation. Okay, you see there is C. Then this equation is actually, we need to copy it because it has not been copied. It has been copied with B4. So your value is there. We are simply copying it throughout your time of simulation. Now we can change the value. Let us consider that we are using a circuit with 1 ohm resistance. That means we have an RLC circuit with 1 ohm resistance, 0.5 ohm inductor, and 3 C equal to 0.1 farad. You see that your voltage across your capacitor is changing in this way. Current through your circuit is going in this way. Okay, in this circuit, actually, in the steady state, what will be the voltage across the capacitor? If we have an RLC circuit with a step source of magnitude 10 volt applied to it, what will be the voltage across the capacitor at the steady state?
Sir, the source voltage.
Source voltage equal to what? How many voltages are there here in this case?
So 10 volts.
So can you see that it is not 10 volt?
Yes, sir.
But you see that your 10 volt is appearing not, for example, in a constant way, something like this. It is changing in this way. What is the name of this type of response in a second order circuit? And why this response is having this nature? Hey, কি পড়ে আসলা তোমরা এই second year electrical circuit? I cannot actually understand what have you learned actually. No viable answer I am getting from you. How many types of responses are there in a second order circuit? I have discussed something in the last class also. Okay, one is critically damped. Hey, please be fair. Okay, did you heard this name for the first time, or you have heard this name earlier? Have you heard this name earlier?
Yes, sir.
Among these three categories, which category this response belong? Hey, if someone will ask you to write the general equation of this voltage VC, what will be the shape of the general equation? Okay, fine. Now your L value is there, 0.5 Henry. Your C value is there, 0.1 farad. Your R value equal to 1 ohm. You have your two roots of the characteristic equation that actually characterizes the solution is equal to minus R divided by 12 plus square root of R by 12 square minus 1 divided by square root of LC square, something like this. Can you calculate? Okay, yeah, you have your calculator. Okay, calculate the value of the real part. Calculate the value. Do it. Your RLC values are given there. Hey, don't you have calculator with you? Are you doing something?
Sir, calculating, sir.
Okay, then what is the value of the first term? Minus R. Do you need a calculator to calculate it? It is equal to what? It is equal to minus 1 divided by 2 into 0.5 is equal to minus 1. Is it not minus 1?
Yes, sir.
Then 1 divided by LC equal to what? 1 divided by 0.5 into 0.1 is equal to what? 1 divided by 0.05 is equal to what? It is not equal to 20.
Yes, sir.
Then your roots are what? Minus 1 plus minus square root of 1 minus 20, isn't it?
Yes, sir.
And that is equal to minus 1 plus minus square root of minus 19. Is that root is now is real?
No, sir. It's imaginary.
Then it would be equal to what? This would be equal to minus 1 plus minus j into square root of 19, okay? Then your roots are appearing as complex conjugate, okay? So if we have a root something like this, what will be the general solution? Will not be your general solution something like this e to the power minus t into cosine, for example, say this quantity is square root of 19t plus some phase factor can be there in this form. Then any student of intermediate level can plot it. If we plot it, you will see that that plot will be taking the shape. It will be oscillating with a omega frequency, something like this, and it is exponentially decaying. Is it not, for example, your earlier solution is something like this? It is oscillating and decaying?
Yes, sir.
This is supposed to be explored in your first, second semester, how a system will behave in this way. So this is the name of this response is actually underdamped because it is not damping. It is oscillating and damping towards the steady state value. And you see that sometimes you see that your system may give you some strange result. And I am not actually giving you, try to explore it by your own by changing the values of R, L, and C. And you can change the value of your step size and try to examine that how your current and voltage across this RLC circuit is changing with respect to the value of L. One interesting thing you can observe that if we set the value R equal to 0, you see that your solution is something like this. Will your circuit will reach the steady state? Why your solution is something like this? It is something like sinusoidal.
Yes, sir.
Okay, try to explore it. The why is it sinusoidal? Okay. So when you R equal to 0 in a circuit, RLC, why your response is sinusoidal? And a figure can be drawn something like this. Have you seen this type of figure in your earlier life, even in the laboratory? Have you used any instrument in the laboratory that can draw a figure? Hey, have you seen any instrument in your laboratory of electrical engineering department of IUT in your life that can show you a picture or a figure, something like this?
Sir, oscilloscope.
Oscilloscope. So if you want to see a figure, something like this, a circle in the oscilloscope, in which mode you need to operate your oscilloscope? Because have you seen any circle ever in your oscilloscope? Can anyone tell me what are the information present in the front panel of an oscilloscope? You have a front panel in the oscilloscope. At the top, something is written. We have a reticule there where we can find a picture. Then we have many knobs there, something like this. Can you tell me that how many important things are there written in this panel? Because unless you know this thing, you will never be able to use an oscilloscope. Okay, now you see it is very simple and probably very likely that your physical presence in the laboratory might not be possible in near future so easily. And you had your opportunity earlier. I don't know to what extent you used it, but try to measure yourself that you invested money and time. What is the outcome? You can have many reasons behind it, but ultimate loser will be you, okay? Be careful about that. Nobody will be coming to me to accuse me that you never taught the student. The thing is that this type of figure is actually a circle, okay? If you want to plot a circle from your first year intermediate geometry, can you write the equation of a circle in the polar form? Hey, is it not something like that? you write your equation in this way: x square plus y square equal to r square centered at the origin. And sometimes we write here r into cos theta plus whole square into r into sine theta square. Can you write this in this way?
Yes, sir.
Yes, sir. Yes, sir.
That, what does it mean then? If we change the theta and calculate this value and want to plot it and put, for example, one, for example, in the x-axis and another in the y-axis, would it not be a circle?
Yes, sir.
If we have a circle there, that signifies that in plotting this figure, we used a figure is called a scatter plot. And this axis is, for example, I, and this axis is Y. That this axis is VC. That means one is the current flowing through your circuit, another is the voltage across the capacitor. And you see that if we don't have any R there, if R is equal to 0, the root you have calculated earlier, lambda 1 and lambda 2, that contains a factor R divided by twice L, and another factor there R by twice L square minus 1 by LC. If your R equal to 0, then this real part would be equal to 0. And this part would be equal to 0. Then your lambda 1 and lambda 2 would be equal to what? A square plus minus a square root of minus 1 divided by LC, isn't it?
Yes, sir.
And that will be equal to plus minus J into 1 by LC. If this is your roots are complex conjugate type, something like this, then your solution for voltage current will take the form, say, cosine. If we consider this factor as beta, that's cosine beta t, something like this. Then your VC will also be a factor because you know the relationship between VC and IC. If one is sine, another will be cosine, isn't it?
Yes, sir.
If we plot I there in one axis and V there in another axis, that simply we are putting a sine term in one axis and cosine term in other axis in a XY plot. Then what will happen? Will not be a circle then? If we plot it in the scatter plot. And in the oscilloscope, you have your mode there because in most of the cases, we plot the thing with respect to time because time is the variable. But if you want to plot it in like this, then you have to change your mode to XY mode. In all oscilloscope, there is a mode, it's called XY mode. Have you heard about the presence of XY mode in an oscilloscope? Okay. Then you have your resources there. You cannot live without Facebook. Try to go to the YouTube. You will have lots of things are there in the YouTube for your learning. Even the lecture that I am giving, you will find much nicer lecture there than me because those teachers are from very renowned universities. They are more experienced than me. Okay. I also learn many things from YouTube. I don't know what are you doing. So you can explore your circuit by this thing. You see that if you know resistance is there, a very common sense will be there that inductance cannot consume energy, your capacitance cannot consume energy. Then if no inductance are there in your circuit, then where the, for example, energy will go? The energy will be toggling between inductor and capacitor with a frequency is equal to 1 divided by square root of LC radian per second. And your circuit will take the response of the circuit at that point is called undamped. So we have our 4 categories of responses. One is critically damped, another is overdamped, third one is underdamped, and the 4th special case is undamped. Undamped cases are simple like oscillator. And I hope that when you have been introduced to oscillator, this must be the first lesson. The teacher should talk to you to give an idea how an oscillator works before going to some active devices. You can build an oscillator by using simple L and C. In many of our devices, we use this simple technique in generating some alternating frequencies. That's it from my part today.